Okay, so let's see now an implementation of a multi-layer network from scratch. So we will use MNIST as an example. So we have MNIST is a database of handwritten numbers. So we have many zeros. So I think in total there is something like 60,000 numbers or so. So there are a lot of zeros, a lot of ones, a lot of twos, and you see that each one of them looks different. And we want the network, given one of these images, to recognize which number it is. So the numbers are given, the input vectors are vectors of size 28 pixels. We will call them x, and then for each x we want to construct a network that produces a one-hot encoding of the output. So this is number 9, so it will be 00001. So this is 1 because it is 9. This one represents 8, 7, 6, and so on down to 0. So if you have a 0, then it would be 1, 0, 0, 0, 0. If you have 1, you would have 0, 1, 0, 0, 0, and so on. So we want the network, given one of these images, to produce one of these one-hot encodings. So the code is here. We will see it now in a moment, and this is we will go over the code later. So let's see how it looks like. The execution. So the execution, you can see we start with a high loss function and very low accuracy, and then we run over every epoch is seeing all the numbers in the dataset. So it is learning the numbers and learning to classify these numbers into this one-hot encoding. And in these 15 first epochs, you see that it goes down to, or it goes up to an accuracy of 61. At the beginning it grows very quickly, and then it saturates, meaning that the network, this very simple network, can no longer recognize the numbers better. And actually the optimization is performed on the loss, although we understand better the accuracy. So we as humans understand better the accuracy, although the loss is the one that the neural network is optimizing. So here it is how it is learning. So it has the accuracy as the function of the number of epochs, and the same here. So how the loss function is decreasing. So you see that for the very first, so for the almost the 80 epochs that we have studied here, the loss function is still decreasing, although in terms of accuracy, most of the big changes occur in the first 10 iterations. So let's look at the code of this. So the code starts with the main. So it is a Python code. We will try to have everything inside our code. So no use of external libraries, at least for most of the topic of the things. And then so we start by loading the data, and we can load training data and test data. So we have two separated data sets. Then the input images that are defined between 0 and 255, we divide by 255, so that now they are defined between 0 and 1. And then we compute this one-hot encoding of the output. So we have some labels. These labels are simply the numbers, so 0, 1, 2, 3, and then we construct these vectors, or one-hot encoding vectors of size 10, because we have 10 different digits. So here we have the labels for the train, for the test, This is a reshaping, but typically this is something that the tensors and the tensor multiplications that we use inside our this wx plus b, those are tensors rather than matrices, and then they need an extra dimension. So what we are saying here is reshape it as vectors of this size, so just 1D vectors, and this minus 1 is just to account for as many rows as needed. Yeah, so here train the test, and then here we define the model. The model is a sequential model, so it is a number of layers, one after the other. This class we have defined, we will see it later, and we add the first layer, this 28 times 28 is this 784. So the input to the first layer has 784 input units. It will output 50 neurons. The activation layer is a ReLU, so this is the nonlinear function, and we will initialize following this procedure. We will see all this in detail later. And then the last layer will take these 50 neurons, so this is the input. It will produce 10 outputs. The activation will be a softmax. The activation will be a softmax, and again it will be initialized with this method. Then we set the loss that we want at the optimizer, and we have some scheduling for the gradient descent. So we have this scheduler with this learning rate. We do the fitting with batch sizes of 6,000, so we have 60,000 numbers, and we will go in batches of 6,000, and we will run for 100 epochs. Then this has been done on the training, and then we will predict on the test the predicted ones, and we will compare the two outputs and see if they look similar or not. Actually, I think I forgot to show you this. This is the confusion matrix for this result. So the confusion matrix simply compares what is the ground truth to the predicted, and then counts how many good values you have had, how many good predictions, and then which are the errors. Then you see, for instance, the most difficult numbers to classify. Many 4s have been classified as 9s, and many 9s have been classified as 4s or 7s. So many 9s have been classified as 7s, and many 5s have been classified as 8s. So here you can see the mistakes. Okay, very good. So let's go again over this code and see the different parts of it. So first, we will need these activation functions. So the activation functions, we define them here. So we are defining the hyperbolic tangent, and then we define what is the activation. So remind, this is sigma of x. So the input to the sigma is just the scalar. So this is the definition of that hyperbolic tangent, and then what is the derivative? So the derivative of the activation and then what is for the sigmoid, what is for ReLU, what is for softmax, and so on. Actually, we will see all these in much more detail. We have already seen, I think, in one of the previous lectures. So just for you to see how these things look like. So if I look for the sigmoid function, it is a function that does this thing, and the hyperbolic tangent it is also one of these functions. Okay, so these are the activation functions. We will also need to initialize the layers, the values in each one of the layers. So what we have is we can have different ways to initialize. So we will have an input channel and an output channel. So these are the sizes of the number of inputs, number of outputs, and then we can define what are the values, and we also have to give memory for the derivatives of those values, and if necessary for the speeds. You may remember from the part of optimizers that some of the optimizers they were having momentum, and the momentum was related to the speed. So we may initialize everything with zeros, everything with zeros here, or we can have here, for instance, this initialization, they are random numbers, and this is a random normal, so a Gaussian with 0 mean and standard deviation 1, and here we have some amplitude for the standard deviation, and the He method, that is the one that we have chosen. It is kind of similar to this one, but with a different sigma. So the variance of the initialization is different, and the same for Kumar, or the same for whatever. Then we have a class of optimizers. So the class of optimizers will implement the different optimization algorithms. So for instance, the gradient descent. The gradient descent, we will have a number of layers, and we are optimizing the layer in this index. So the layer in that index will have a weight and a bias. And you may remember from gradient descent that the formulas that we gave before in previous lectures, that it was the current weights minus the learning rate and the derivatives. So this is just gradient descent. RMS prop had a momentum, and then we had some gamma, so some coefficient for the update of the velocities. So it is just this one. So this we take the derivative, and then we compute the squares, and then we update the velocities in this way, and then we update the weights according to the velocities. So you may go back to the lecture with the optimizers to see all this. And then we had the Adam had these formulas, so we had a gamma 1, gamma 2, the derivatives and the momentum, and so on, Adam max. So we have the different optimizers. Then we need to define the layers. So for the layers, we will only define one kind of layer, that is the dense layer. So it is a fully connected layer, and this fully connected layer, you will have to give the size of the input, the size of the output, what is the activation, and what is the initialization. If we go down again to the code, we see that when we define the layer, so we say layers, dense, this size of input, this size of output, activation, and initialization. So we are calling this function, if I can find it, yeah, here. So we are calling this function, this is initialization, with these parameters. So we are just keeping the initialization, we are defining the internal weights, biases, the derivatives, the momentum, and depending on what is the kind of initialization, we are initializing them in different ways. And then yeah, we haven't seen the class model, no? The class model is later. So what we are doing here is we are adding for each one of the models so for each one of the layers we will have an activation layer. So we will add this one, and then we have to say how to do the forward processing and the backward processing. So this part, you see, it is just the computation of set, so just the linear part. So it is the multiplication of x times the weight. So in our formulas it is more convenient to write w times x, but depending on how you store your matrices, you may store the transpose, and then it is simply x times w. So and then plus the bias. So this part is just computing the linear part, and then we have the backward. So what is the derivative of this with respect to w? So the derivative of this computation with respect to w, it is x transpose. Then, okay, so what is so this model here? So this model here, this model is a global variable, I think. It is global. Okay. Otherwise, this model is one of these of this kind, sequential. Okay, so let's see how the sequential works. So the sequential will have a list of layers, a list of activations, a list of loss functions, epochs, and accuracies. So we will. This is just for keeping track of what is the loss functions for each one of the epochs, and the same for accuracy. So when we are adding down here, so when we are adding the layer, so this layer here, so we will be calling this function. So we are simply keeping all the layers in a list, and then we had the loss function. Okay, so we have the loss functions and the optimizers. The optimizers we have already seen, and the loss functions we have not seen. So we have here the two possible loss functions. One is for categorical cross entropy, that is the one for multiple outputs, and binary cross entropy if you have just two outputs. So we are using this one because we have 10 different classes. So we have what is so we have what we want to predict, and what we have predicted, and what are the true values. So here we have the forward loss. So for the forward loss, takes the number of classes that we have, so 10 in this case, and the loss function is this one. So it is the logarithm of the predicted value times the true value. So this true value will be 0,0001, and this one will be a number between 0 and 1. So these ones will be numbers between 0 and 1. We would like all the zeros here, to be predicted by very small numbers, and all the ones here, just one of them, to be a very high predicted value. So let's say 0.99. So the logarithm of 0.99 is 0, or very close to 0, while the logarithm of all all these values close to 0 will be very negative. And then we are adding and computing the average over this number of classes. And then we have to say how to compute what is the error that we have to backpropagate. So the error will be the difference between the predicted value and the true value. And we will not comment this binary cross entropy because we are not using it, but it has the same spirit as this one. Then what else are we doing here? So we define a sequential model, we add the layers, we compile it. So compile means we can see, so we can see this function. This function is simply taking note of which is the loss function, which is the optimizer. So we can go back, then the scheduler. So the scheduler, this again, just taking a note. So taking a note of what is the learning rate, and if we have a more complicated scheduler, what would be the scheduling for the learning rate. And then we have the fitting. The fitting is the actual function that does something. So this fitting, you can see it here. So we have the cost function, cost and accuracy as globals. We don't care about that. Then we have the number of epochs, so we will iterate over the number of epochs, and then this is just for measuring time. And what we will do is to take a batch. So all this part is taking a batch. So we know which batch it is. So with this loop over the number of batches, so this is the 60,000 elements in the database. Then we divide it in number of batches, and this is the batch number. So these two are the indexes of the first and last vector in the training and in the outputs that we have to take. So now this A will be the input to the first layer, and this Y will be what we want to predict. So now what we do is we iterate over all layers. So for each layer we compute the linear part. So the linear part is just the forward of Wx plus V, and then we keep all of them along the different layers. And then we have the activation part, the non-linear part, and we also keep them. And then we have a cost function. So depending on what is the kind of cost that we have to evaluate the cost function. So here we have the loss, and the loss is just the cost function evaluated for this last value. You can see this is the last value here. So this is our final prediction in the last layer compared to what we want to predict. So this is the ground truth. And then we have the back propagation. So we have the difference, and we have to update. So the update, we keep the derivatives of each one of the layers. So the derivatives are these derivatives here, and we update, we keep this deliver delta that will be updated over the different layers. And you see that we are going from the last layer to the first layer. Very good. Okay, and then we have to update the parameters. So we know how much we have to update. So these are these calculations that we were doing the other day. So the other day we were, it was here. So we were propagating this delta, we were propagating it backward in the different, through the different layers. So we are updating what we have to, so these are the deltas that we have to update. And then the optimizer decides how to update that layer. So here you see you are updating this layer, so the layer number 1, number 2, and with this learning rate, and then these derivatives that have been calculated here, and then you have the moment and you have the learning rate. So this we have seen before. It was part of the so this is the coefficient to update the internal momentum, and the same applies to Adam, Adamax, and so on. And then we compute the accuracy. So here is the accuracy of how many of them are the same, and we iterate for the next batch. So after every batch, we are updating the layers, the weights of the layers. So we have a batch, we compute the cost and the loss function. So from the loss function, we compute the delta, that is the final error, and this final error as a vector, we back propagate using this optimizer, and then we go for the next batch. And when we have finished with all the batches, then we go for the next epoch, and then we go it again over the whole input data set, and then we have the plots and so on. Okay, so now let's say that we have already trained. So if we have already trained, then we can predict. So this is called the inference. So now we can use the trained model to predict what the function will be, so what the classes will be for this test data that we have never seen before. So the prediction, it is just a very, very simple loop in which we this is the input, so these are the input images, and then we propagate the input images through the different layers. So we have the linear part, and then the linear part goes through the activation function of these so for each layer. So you can see that each layer can have its own activation function, and actually here we made use of that. So the first layer has a ReLU function, and the last one has a softmax. And we have seen here the results. So it is not a very good. So what is it? I think this is back propagation. Okay, it is here. So it is not an excellent model. So very simple model with just 50 neurons in the hidden layer, not too deep, just to a couple of layers. But it is very easy to track and to understand what is happening through the network. So with this we finish this session, and we will see you in the next one.